Welcome to Wave Particle Duality, Physics 30 lesson. Now, when we talk about the wave properties of light, the first one we usually think of is reflection. That idea that waves will bounce off of one thing and reflect. We also think of refraction, that bending of waves as a transport from one medium to another. This is something else light does. And diffraction, that concept that waves will in fact diffract, and light also produces this pattern. This led to the idea that light was indeed a wave. However, some of the particle properties of light included the ultraviolet catastrophe. This led to Max Planck's quantum hypothesis that these waves did not build up, but in fact were in little tiny doses. Led to Einstein's discovery of the photoelectric effect, causing electrons. And we also have the Compton effect, that fact that waves, in fact, do obey the laws of conservation of momentum. The wave properties of light, we got reflection, refraction, and diffraction. Particle properties of light include Planck's hypothesis, photoelectric effect, and the Compton effect. And light has both these wave and particle type properties. So just as an example, again, what is the momentum of green light? Well, the momentum is h over wavelength. We will take 6.6, make my decimal a little bit bigger there, 6.63 times 10 to the negative 34 joule seconds over 5 times 10 to the negative 7 meters. That gets you a momentum of 1.33 times 10 to the negative 27. And because all of this is standard units, we can actually say this is kilogram meters per second, even though green light is massless. Give this one a try. What is the momentum of light with the frequency of 5 times 10 to the 14 hertz? Pause the video now and let's see how you do. Taking that formula that we used in the last example and the universal wave equation to combine to find this HF over wavelength. Now you could have done this where you found the wavelength and then just put it into the universal wave equation to find the frequency. That would have worked just as well. But you should have ultimately came up with 1.1 times 10 to the negative 27 kilogram meters per second. Or you could have said Newton seconds or joule seconds per meter. Now, de Broglie's wave hypothesis proposed that all matter exhibits wave-like properties and particle-like properties. It relates to the wavelength of its matter to its momentum. After Albert Einstein's photon theory became accepted, the question became whether this was true for light or the material objects as well. Now, particles do indeed have wavelengths too. Particle a wavelength. We call it a Broglie wavelength. Matter is found to have the same interference characteristics as other waves, but small particles such as electrons at high speeds best exhibit this property. Here we see the electrons coming through, exhibiting a diffraction pattern. Now the thing is that really we only see this with small particles because they're the only things that we have that exhibit around that the proper wavelengths and diffractions and whatnot. So we're going to have a short little video here to kind of explain that.
The granddaddy or little balls of matter. If we randomly shoot a small object, say a marble, at the screen, we're going to see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see the second band duplicated to the right.
Now, if we add a
the
second
waves
slit, we would
the
expect to
waves
see
hit
a
the slit
second band
and radiate
duplicated
out,
to the right.
striking the back wall with the most
Now,
intensity directly
look at
in
waves.
line with the slit.
The waves hit
The
the
line
slit
of brightness
and
on the back
radiate
screen
out,
shows
striking
that
the back
intensity.
wall with
This
the
is
most
similar to the
intensity
line the
directly
marbles
in
make.
line with the
But
slit. The
when
line
we
of
add the
brightness on the
second
back
slit,
screen shows that
something
intensity.
different happens.
This is similar
If
to
the
the
top
line
of one wave
marbles make.
meets the bottom of another wave,
When we add
they
the
cancel
second
each other
slit,
out.
something
So now
different happens.
there is an interference
If the
pattern
top
on
of
the
one
back
wave
wall.
meets the
Places
bottom
where the
of
two
another
tops
wave,
meet are the
they
highest
cancel each other
intensity,
out.
the bright lines,
So
and
now
where they
there is
cancel,
an
there is
interference
nothing.
pattern on the
So,
back wall.
when we throw
Places where the
things,
two
that
tops
is,
meet
matter,
are the highest
through two
intensity,
slits,
the bright
we get
lines,
this.
and where they
Two
cancel,
bands of
there
hit.
is nothing. So,
And with
when
waves,
we throw
we get an
things,
interference
that
pattern
is,
of many
matter,
bands.
through two slits, we get
So
this.
far, now,
Two bands of hits.
let's go
And
quantum
with
mechanics.
waves, we get an interference pattern of many bands.
An
Good,
electron
so far.
is a
Now,
tiny bit
let's
of matter,
go quantum.
like a tiny marble. Let's fire a stream through one slit.
An electron is a
Just
tiny,
like the marble,
tiny bit
a
of
single
matter,
band.
like a tiny
So,
marble.
if we shoot these
Let's
tiny
fire a
bits
stream
through
through one
two
slit.
slits, we should get,
It behaves
like
just
the marbles,
like the
two
marble, a
bands.
single band.
What?
So, if
An
we shoot
interference
these
pattern.
tiny bits through
We
two
fired
slits,
electrons,
we should get,
tiny bits
like
of
the
matter
marbles,
through.
two bands.
We get a pattern like waves,
What?
not like little marbles.
An interference pattern.
How?
We fired
How did pieces
electrons,
of matter
tiny
create
bits of
an
matter
interference
through.
pattern like a
We
wave?
get a pattern like
It
waves,
doesn't make
not like
sense.
little marbles.
But physicists are clever. They thought
Pieces of matter
maybe those
create
little
an
balls are
interference
bouncing off
pattern
each
like a
other
wave.
and creating that
It
pattern.
doesn't make
So,
sense.
they decide to shoot the electrons through one at a time.
Maybe
There is
those
no
little
way
balls
they
are
can
bouncing
interfere
off
with
each
each other.
other and creating that pattern.
But after an hour of this, the
They
same
decide to
interference
shoot the
pattern
electrons
seems to
through
emerge.
one at a
The
time.
conclusion is
There is no
inescapable.
way they could
The
interfere
single
with each other.
electron leaves as a particle,
After
becomes
an
a wave
hour
of
of this,
potentials,
the same
goes
interference
through
pattern
both
is
slits,
seen to
and
emerge. The
interferes
conclusion
with
is
itself
inescapable.
to hit the wall
The
like a
same
particle.
electron leaves
But
as a
mathematically,
particle,
it's even
becomes
stranger.
a wave of
It goes through
potentials,
both
goes
slits,
through
and
both
it goes
slits,
through
and
neither.
interferes
And it
with
goes through
itself
just
to
one,
hit the
and it
wall
goes through just
like
the
a
other.
particle.
All
But
of these
mathematically, it's
possibilities
even
are in
stranger. It
superposition
goes through
with
both
each other.
slits,
But
and
physicists
it
were
goes
completely
through neither.
baffled by this.
And it goes
So
through
they
just
decided
one,
to
and it
wait
goes through just the
and see
other.
which slit
All of these
actually
possibilities
goes
are in
through.
superposition with each
They
other.
put a
The
measuring
physicists
device
were
by one
completely
slit
baffled by
to
this.
see which one it
So
went
they
through
decided to
and
compete
let it fly.
and see which slit
But
actually
the
goes
quantum
through.
world is far more
They put a
mysterious than
measuring
they could have
device by one
imagined.
slit to
When
see
they
which one it went
observed,
through
the electron
and
went
let it fly.
back to behaving like a little marble.
But the
It
quantum
produced a
world
pattern
is
of two
far more
bands,
mysterious than they could have
not an
imagined.
interference pattern
When
of
they
many.
observed, the
The
electron
very
went back
act of
to
measuring
behaving like a little
or
marble. It produced
observing
a pattern of
which
two
slit it
bands,
went through meant
not
it
an
only went
interference
through
pattern
one,
of many.
not both.
The very
The
act of
electron
measuring
decided to
or
act
observing
differently.
which slit it went
So
through
it was
meant
aware
it only went through
it was
one,
being
not
watched.
both.
It
The
was here
electron
that
decided
physicists
to
stepped
act
forever into the
differently,
strange, never world
as though
of
it was
quantum
aware
events.
it was being watched.
Marbles
And
or
it was
waves?
here that
And
physicists
waves of what?
stepped forever into the
And
strange,
what does an
never
observer
world
have to
of
do with
quantum
any?
events. What is matter?
The observer
Marbles or
collapsed
waves?
the wave function
And waves of what?
simply
And what does
by
an observer
observing.
have to do with any?
So if electrons also have wavelengths, we should be able to find out both the momentum and wavelength of an electron traveling at this speed of 1.5 times 10 to the 4. Well, the momentum part should be relatively easy. We've done this before, the mass of the electron being 9.11 times 10 to the negative 31 kilograms. The velocity it's moving at is 1.50 times 10 to the 4 meters per second, and therefore is 1.37 times 10 to the negative 26 kilogram meters per second. If we want to find its wavelength, we're going to now go to this equation, h over p, right? Just as if it were, in fact, a photon. And so the wavelength is 6.63 times 10 to the negative 34 joule seconds over a momentum of 1.37 times 10 to the negative 26 kilogram meters per second. We find that wavelength of the electron is sitting in the neighborhood of 4.85 times 10 to the negative 8 meters. Now, this is a little bit shorter, but this would in fact be within the UV range of if it were light. But it's not light. It's not electromagnetic radiation. This is an electron. Okay, so pause the video and try this for the muon particle. Mass is 1.88 times 10 to the negative 28 kilograms, moving at a speed of 3.2 times 10 to the 6 meters per second. Pause the video, give this a try. Okay, welcome back. Momentum again, mass times velocity, 6.02 times 10 to the negative 22 kilogram meters per second. And using that momentum, you can find the wavelength, wavelength being Planck's constant divided by momentum, or 1.10 times 10 to the negative 12 meters. The Heisenberg uncertainty principle states that the velocity and position of an object cannot be measured exactly at the same time, even in theory. Now, for this, we use this formula where delta x, delta p, according to is proportional to h squared. Now, this is not a formula that's really a formula. It's just to reinforce the concept of the uncertainty principle. And basically, this idea of measuring winds up breaking down the wave function, and therefore you cannot know both. Delta x representing the uncertainty within the position. Delta p being the uncertainty within the momentum, and thus the velocity. Okay, and again, this is purely just to reinforce the concept. Let's take a look at a video to kind of understand this a little bit further before we go to a couple of examples.
The Heisenberg uncertainty principle is one of a handful of ideas from quantum physics to expand into general pop culture. It says that you can never simultaneously know the exact position and the exact speed of an object, and shows up as a metaphor in everything from literary criticism to sports commentary. Uncertainty is often explained as a result of measurement, that the act of measuring an object's position changes its speed, or vice versa. The real origin is much deeper and more amazing. The uncertainty principle exists because everything in the universe behaves like both a particle and a wave at the same time. In quantum mechanics, the exact position and exact speed of an object have no meaning. To understand this, we need to think about what it means to behave like a particle or a wave. Particles, by definition, exist in a single place at any instant in time. We can represent this by a graph showing the probability of finding the object at a particular place, which looks like a spike. 100% at one specific position, and 0 everywhere else. Waves, on the other hand, are disturbances spread out in space, like ripples covering the surface of a pond. We can clearly identify features of the wave pattern as a whole, most importantly, its wavelength, which is the distance between two neighboring peaks, or two neighboring valleys. But we can't assign it a single position. It has a good probability of being in lots of different places. Wavelength is essential for quantum physics because an object's wavelength is related to its momentum, mass times velocity. A fast-moving object has lots of momentum, which corresponds to a very short wavelength. A heavy object has lots of momentum even if it's not moving very fast, which again means a very short wavelength. This is why we don't notice the wave nature of everyday objects. If you toss a baseball up in the air, its wavelength is a billionth of a trillionth of a trillionth of a meter, far too tiny to ever detect. Small things, like atoms or electrons, though, can have wavelengths big enough to measure in physics experiments. So if we have a pure wave, we can measure its wavelength and thus its momentum, but it has no position. We can know a particle's position very well, but it doesn't have a wavelength, so we don't know its momentum. To get a particle with both position and momentum, we need to mix the two pictures to make a graph that has waves, but only in a small area. How can we do this? By combining waves with different wavelengths, which means giving our quantum object some possibility of having different momenta. When we add two waves, we find that there are places where the peaks line up, making a bigger wave, and other places where the peaks of one fill in the valleys of the other. The result has regions where we see waves separated by regions of nothing at all. If we add a third wave, the regions where the waves cancel out get bigger, a fourth and they get bigger still, with the wavy regions becoming narrower. If we keep adding waves, we can make a wave packet with a clear wavelength in one small region. That's a quantum object with both wave and particle nature. But to accomplish this, we had to lose certainty about both position and momentum. The position isn't restricted to a single point. There's a good probability of finding it within some range of the center of the wave packet. And we made the wave packet by adding lots of waves, which means there's some probability of finding it with a momentum corresponding to any one of those. Both position and momentum are now uncertain, and the uncertainties are connected. If you want to reduce the position uncertainty by making a smaller wave packet, you need to add more waves, which means a bigger momentum uncertainty. If you want to know the momentum better, you need a bigger wave packet, which means a bigger position uncertainty. That's the Heisenberg uncertainty principle, first stated by German physicist Werner Heisenberg back in 1927. This uncertainty isn't a matter of measuring well or badly, but an inevitable result of combining particle and wave nature. The uncertainty principle isn't just a practical limit on measurement. It's a limit on what properties an object can have, built into the fundamental structure of the universe itself.
All right, so let's take a look at this example here. Delta x, delta p is kind of proportional to h squared. That should be an h squared. Okay, we're looking for the uncertainty in the momentum. We've got the location within 2.3 nanometers. And so we're going to divide both sides by delta x. So delta p is equal to h squared over delta x. And really we shouldn't put equal to, proportional to. So delta p, 6.63 times 10 to the negative 34 joules seconds. That's going to be squared, divided by 2.3 nanometers, or 2.3 times 10 to the negative 9 meters, gets you an uncertainty of momentum of 1.9 times 10 to the negative 58. Uncertainty of momentum, we had joules squared, seconds squared, meters squared. So we should wind up with the uncertainty being somewhere in the neighborhood of joules squared, seconds squared over meter squared. No, not meters squared, just meters. Give this one a try. Pause the video and just see how you do with this one. Hey, welcome back. And again, delta x, delta p, proportional to h squared. Dividing both sides by x squared gets you an uncertainty of approximately 1.1 times 10 to the negative 56 joules squared second squared per meter. To kind of summarize this all, we're going to take a look at a little brief history of quantum mechanics in a third video within a video.
Traveling to the 1750s, we find that scientists were putting different substances in flames and passing the resultant light through a prism. They found that the hot gases given off by the burning materials emit different colors of light or spectra. For example, ordinary table salt generated a bright yellow spectra. Furthermore, not all the colors of the rainbow appeared. There were dark gaps in the spectrum. In fact, for some materials, there were just a few patches of light. By the 1820s, they recognized that spectra provided an excellent way to detect and identify small quantities of an element in a powder that was put into a flame. Meanwhile, the white light of the sun was also being examined closely. And in 1802, it was discovered that the solar spectrum itself had tiny gaps. There were many thin, dark lines in the rainbow of colors. But the reason for spectral lines in the light and the relationship to each substance was a real mystery. Traveling forward from that era to a little over 100 years ago, scientists were examining the colors of light given off by solid heated objects. They discovered that these hot solids gave off continuous spectra, and that the overall color of the light revealed the temperature of the object. Now, this was important because scientists realized that this discovery made it possible to measure the temperature of an object from a distance. They could measure the temperature of the sun, for instance. During these discoveries, they also noticed that some of the objects absorbed light extremely well, almost perfectly in fact. They were called black bodies because they absorbed virtually all the light that was shown upon their surfaces. These same objects also radiated almost perfectly, and as noted before, the temperature of the black body object determined the distribution of colors or wavelengths in the emitted light. This curve shows how much light of each color is emitted by a cool object. As you can see, there isn't much light, and what light there is mostly lies out past the red end of the spectrum, in the infrared. The figure on the right will show the different colors added together as we progress. Right now, only red light is visible. This curve shows how much light of each color is emitted by a medium temperature object, and the most light is emitted in the orange, yellow, green wavelengths. So now we add orange, yellow, and green to our cauldron of light on the right. As you can see, the combination so far looks yellow. This third curve is for a really hot object. Lots of light, and with most of it being emitted toward the blue end of the spectrum. And as you can see, our cauldron now is pure white in the center where all the colors overlap. A heated black body follows this color path as the temperature rises. A good example of black body radiation is the heat inside a kiln. Inside the kiln, electromagnetic radiation, light and heat, exist in a form of standing waves. Waves that, like the vibration of a guitar string, are attached at both ends. The ends of the standing waves, like the ends of a guitar string, do not move. They are anchored to the sides of the kiln. And many waves exist with varying wavelengths of color. At low temperatures, the primary color inside the kiln is the infrared, and we cannot detect it with our naked eye. But as the temperature rises, the kiln begins to glow red, and as the temperature continues to rise, the dominant color changes to orange, then yellow, then bluish white. The distribution of energy in light shifts to shorter wavelengths as the temperature rises. But there was a problem. The scientists expected the distribution of emitted light to continue to the increase at wavelengths toward the ultraviolet end of the distribution. It didn't. Instead, there was less and less light given off as they were further and further into the ultraviolet. This was called the ultraviolet catastrophe. But it wasn't a catastrophe at all. It was the beginning of something remarkable. A truly great scientist named Max Planck soon figured out a way to explain the observation. He concluded that the energy contained in the standing waves inside the kiln did not and could not possess just any and all different amounts of energy. Instead, the quantity of energy these standing waves possess had to be limited to a few specific discrete values of energy for each color. A standing wave of blue light, for example, can have energy equal to 0 electron volts, or 3 electron volts, or 6 electron volts, or 9 electron volts, and so on. In general, energy equals any whole number, n, times Planck's constant, h, times the frequency of light, nu, which for blue light is any number times 3 electron volts. But notice, blue light standing waves cannot contain energy equal to 1 electron volt, or 2 electron volts, or 4 electron volts. Realizing that energy could have only discrete values was the beginning of quantum mechanics. The energy is said to be quantized, and n, from the equation above, is called a quantum number. Planck's conclusion that light energy is quantized was quickly used by Einstein to explain another puzzling phenomenon. It was known that shining a light upon a metal plate can release electrons from the plate. But the light has to have a certain wavelength before a single electron is released. We can shine brighter and brighter light on the plate forever, but if the color isn't right, the electrons stay home. Einstein concluded that the light striking the plate had to be coming in discrete bundles, and unless a single bundle had enough energy to free an electron from its captivity, it would remain trapped. And as Planck had suggested, the wavelength and frequency of the light was a measure of the amount of energy each bundle carried. So while blue light packets might be able to free an electron, red light packets could not, no matter how many red packets hit the plate. But wait a minute. That sounds awfully like light is a particle and not a wave. And there are mountains of data showing light behaving like a wave. Diffraction, refraction, interference. Which is it, a particle or a wave? It is both. These light packets are extremely tiny. Let's call them photons, from photos, the Greek word for light. And when you try to explain the behavior of things this small, you must resort to really unusual ideas. the ideas contained in quantum mechanics.
So in summary, there are limits to what we can know about both the position and momentum of a particle as well as a wave. And that's due to the fact that there are both wave and particle natures in everything. Photons have both wave and particle properties, and particles also have both wave and particle properties. I hope that helps. If you have any questions, please let me know, and take care, everyone.